So for next Monday, so consider a spring with a spring constant K, a mass M at the end. So this is the spring, this is a side wall. And the mass is subject to a drag force, Fv, proportional minus the velocity, and a driving force, Fd, that is periodical. So it's similar to the two problems we solve on Wednesday, but they are combined. So you have both. So it's an harmonical oscillator that is both driven by an external force and also dragged by some friction. Okay. So as I said, we solve the two problems independently, and as an exercise, we solve together. On Monday, we put them together and we find the solution. Okay. So that was for the, and then number 2. So consider two masses. So consider two masses. Okay. So I guess you can take them equal, two masses with two equal masses, M, and connected to each other and to the side walls by 3 springs. So connected to each other and to 2 walls by 3 springs. Okay, so it's something like this. No. So you have the 2 side walls, 3 springs, and 2 masses. Okay. So find the most general solution for the positions of the masses as a function of time. And then, what are the normal coordinates? Well, you don't know yet what that is, but it's what we are going to do today. So what are the normal coordinates and normal modes? And 3, 2 pendulums or penduli, I don't know, of equal masses and lengths are connected by a spiral spring. They move in a plane, okay? And the coupling is weak. Find motion with, meaning the trajectories, with small amplitudes. Okay, so here is, you have 2 penduli, and they are connected by a spring. Okay, so call the spring constant K. They have the same length, the same mass. Okay, you have G, and you have to find the solution, that the position of this mass and this mass, so called this 1 and 2, as a function of time. Okay, so those are, and I also, so these are the 3 problems, plus the one I gave you on the quadratic potential in the central force problem, and we solved them on Monday. Did you? You got this one? Can I erase this? Not this. Not even the first one. Okay, then we wait. Hi. Ask if you can't read my handwriting, ask me. So I do the translation where it's not clear. This, find the most general solution for the positions of the masses. Believe it or not. Where? Consider 2 masses and consider 2 masses M, so the same mass, connected to each other and to the 2 walls by 3 springs. Okay, but you don't need it. I did the drawing. So this describes by words what I draw here. You have 2 walls and 3 springs, and in between you have 2 masses. And I guess you can take, let's see. And okay, they have the same spring constant, just to make your life easier. And mine too. Okay, so, okay. So really, all you need are the pictures, right? So here I want x1 of t, x2 of t, or theta 1 of t, depending on what you take as your generalized coordinate. Connected by a spiral spring. Okay, this is by a spring. That's this thing here. What? Find the most general solution for the positions of the masses. What are the normal coordinates and normal modes? Now, you don't know what that, maybe you do, but I haven't told you yet what these 2 normal coordinates and modes are, but clearly this is what I hope, if you finish copying this is going to be explained today. This we cut, I guess, or are you recording it? Just, I don't think it's very, yeah. And also this 1 over r square, is that what you are asking? No, so sorry.
Okay, if you are working on a system, it's equivalent, it's not almost equivalent to harmonic distribution, it's equivalent to it with a lot of projections. So
No, wait, it's not completely equivalent to?
Yes.
To what? To spherical?
No, to harmonic distribution. So we can solve it, but with a lot of projection to the equation of harmonic distribution.
Yes.
So
These are all harmonical oscillators, but they are coupled.
okay.
That's
so
the trick.
We essentially can't use harmonic distribution because we have to add a lot of projections. And the question, how we can use the harmonic distribution equation to make predictions?
No, I mean, what predictions? I mean, it just these are harmonical oscillators. Just they are coupled, and that's what I'm going to explain today. So, how you deal with a bunch of harmonical oscillators that are coupled. Then, if you solve that, you have the trajectories, and is that no? Then I didn't understand. Sorry.
I'm asking because we can, it's a simplest way, because we have exactly the solution of harmonic oscillators. So
Yes.
if we have any situation, we can start with the harmonic oscillator.
Correct.
Okay, so if our system is obey the harmonic oscillator going through a lot of corrections, so
A lot of
corrections.
corrections. So it's not really an harmonical oscillator.
Yes.
Okay.
So in this situation, we can't exactly use a harmonic oscillator equations.
Plus some perturbation.
Yes. And my question, how we can make predictions for this system out of harmonic oscillators?
No, I mean, you know the solution, the unperturbated solution, and then you do the perturbation and see how that is different. So if you have the free solution that is a periodic motion, then if you have some perturbation, as long as the perturbation is small, it's going to be more or less the same solution, but a little different.
Okay, so essentially, any system we can...
No, not any system. All systems that for which the difference with respect to the harmonical oscillator is sufficiently small that you can treat it as a perturbation.
Yes, that's my question.
Yeah.
If it's low, it's
Well, no, then it's a different problem.
yes, different, but we can use a harmonic
No.
oscillator to make... No.
Well, I mean, if it's completely...
There's predictions about the...
No, because if it's so different, the zero order approximation is not the harmonical oscillator, so then you have to start. So if it's so different, it's going to be a completely different solution. Can I, are we, no? You want to ask me what? Two penduli of equal masses and lengths are connected by a spring. Oh, come on, guys. I mean, just draw the picture and it's obvious what the question is, right? I think you don't need to copy what I wrote. I mean, you have the picture, so the drawing tells you what you are supposed to find out. Okay, come on. So already from these problems, you see what the next step is, right? We discuss the harmonical oscillator, then we sort of generalize that solution when you had drag, frictions, whatever. Then when you drive the harmonical oscillator with an external force, and we study the case like this one, in which is periodic. Now the next question is maybe you have a system that, so these were just, so to speak, one-dimensional problems, right? We only had one generalized coordinate. What happens if you have a more complicated system like this one or that one, in which you have more degrees of freedom, more degrees degrees of freedom, but still the potential is anyway some sort of complicated but harmonic oscillator-like potential. So the nice thing is that because the differential equations that these kind of systems give rise are still of the kind we discussed, that is differential, ordinary differential equation with constant coefficients, right? So we still know how to solve them. The difference is that it's not going to be a single equation. Unfortunately, it's going to be a system of equations, right? So a little bit more complicated, but still within the range of the equations for which we know the exact solution. So let's see how this works. you understand that there are many physical systems that are well approximated by this kind of toy models are called, right? Because it's like what a little kid do. For instance, the atomic structure of matter, right, is to a good degree of approximation well described by a bunch of atoms near their equilibrium positions, and when they move away from this position, they are interacting with the potentials due to all the other atoms, and you understand that to a good approximation, that is like the one we described. I mean, it's pulled back to the equilibrium position by a force that is proportional to the amount by which the single atom has moved away from the equilibrium position. So you are back to a sort of harmonical oscillator. The difference is that it's not moving just on a line, it can move in space, so you have sort of three differential equations coupled, but still they are of the form that we discussed. So what that means? We wrote the Lagrangian for the single particle in a harmonical oscillator-like potential, right, that is attracted by or repulsed by a force that is proportional to displacement. It's easy to generalize this situation. What changes is that your potential, you remember, everything started from writing our potential sort of near the equilibrium point, right? Minus k over 2, that was the 1/2, the second derivative of this potential, the displacement, right, something like this, plus, so doing the Taylor expansion. Yeah. So you see that we did it on Wednesday for one generalized coordinate, but I can easily think of the potential as a function of n generalized coordinates, say q1, qn, right? And then all I have to do is to expand about an equilibrium position that I identify by, I don't know, q01, q02, q0n. So this is the equilibrium position. Then you have a bunch of partial derivative, first partial derivatives, but because of the definition that this is an equilibrium point, they vanish, and so you have a 1/2 what? Well, you don't have just a single constant, because now here you have a derivative of your potential, say I and j, right? You have so you call this kij, and you have a matrix of this, because depending in which direction you move, you have a force pulling you back to that position, and that proportionally to the qi minus q dot I, qj, qj plus higher order. All right? I mean, I'm just generalizing what we did on Wednesday to a system that has n degrees of freedom. So you see that in general, what I can do is to write my Lagrangian, So I have some masses, and the masses too, your system in general may have a different mass in a different direction, right? Because the mass is sort of the inertia that your system has. It may be different in one direction or in the other. So masses too, you can think of them as matrices, right? And if I call my generalized coordinate x, let me do, so you have a sort of velocity that is a matrix as well. And then I have that potential, right, that is going to be kij, that matrix. So I call this xi, this xj, that is the amount of the displacement from the equilibrium position, and this is the generalization of what, so in 1D, we had m x dot square minus 1 k half x square, right? Now, in n dimensions, or with n, so this was 1 degree of freedom, with n degrees of freedom, the generalization is this. And because of the definition, these are matrices, okay, and they are symmetric. That means that MIK is equal to MKI. And KIJ, again, is symmetric too. So they are symmetric matrices, okay? Okay, so now I just do what I did for the one-dimensional case, and I write my Lagrange equations, right? And I'm going to have many, because I have many n, in fact, degrees of freedom. But each of these equations, so how do they look? I take the usual, so okay, let's do it. dl dx dot, right? Let's say I, so I take the derivative with respect to the I velocity, so I get this, whatever is here, right? So I get m I k, these are constant, x dot k, right? Remember the Einstein, I'm using the Einstein, so maybe I should write here a sum ak, sum ak. So here I have a sum over k. Remember that if you repeat indices, we agree, that means that I'm summing over those indices, okay? Do you remember this? So if I write this, means that I'm summing over k, and I still have a free index, and that matches this one. That's something that you must become, I mean, as you deal with tensors, that is matrices, always you have to check that indices, free indices, must match from the left-hand side with the right-hand side. Otherwise, there is a mistake. You see, here I have a free index, and here I have a free index. K, it doesn't count because it's sum. In fact, I can change the name of K, right? I can call it J. It will be exactly the same thing, okay? K, yeah, you're right. Sorry. Well, actually, let's do it. That is, I like K better than J. But okay, you are right. I mean, if yes, sorry. Thank you. So that's the first, and then dl dxk. So the partial derivative of your Lagrangian with respect to the k coordinates. You see that you only have here the k, so it just gives you these terms here, that is k I, I'm sorry, I'm taking the I, so I should take a I here. So k I k x k, right? And again, I have a sum over k. So what happened to the 1/2 factor? So you may ask, or it's obvious that I did the right thing. Because this is a symmetric matrix, right? So first you hit one, you are going to have the I component first here, but then the other half of the matrix has the same component there, so you get it twice. So that takes care of the 2 that is gone. If you may have before you wonder about that on Sunday evening. And the equation, I just take the second, the time derivative of this term, and I get finally my Lagrange equation. So they are just MIK, then I hit this with the time derivative, so I get 2 Newton dots. And the Lagrangian, right, is this minus this partial derivative, so this minus become a plus. Actually, this k should be, I mean, okay. Equal to 0. Where I, right, this, so you have, this is one equation, and you have i's of this, where I is 1, 2, I don't know, s or n, the number of generalized coordinates. So as I said, this is a set, a system of S. So this S is equal to the number of degree of freedoms. So this is a system, one for each degree of freedom, but you see they are all, these are constant coefficients, so you see they are ordinary differential equations with constant coefficients, and you know that there is a general technique to solve this kind of problems. That is just a slight generalization of what we have done for the case of the one-dimensional. That, of course, is included here. If I is equal to 1, you have only one equation here, and we are back to our one-dimensional example of Wednesday. All right? So let's see how we solve this. Well, we solve it the same way we solve it. So I take my solution x of k to be this an exponential, right, with some amplitude that I call big A of k, and then some exponential of a given frequency, omega, and then the problem, you see, is the usual things that when you plug this in, what is a differential equation becomes by magic a algebraical equation, right? This is the idea that Fourier had, and we are still banking. We are still banking on Fourier ideas because a lot of differential equations are solved by this trick. That is, this is the simplest form of Fourier transform, right? And it's a very neat trick because we know how to solve algebraical equations much better than we know how to solve differential equations. So if you connect the two, then it's a great idea, no? If he had the, okay. So I take this solution, I substitute the solution in my differential equation, and what I get for this equation, I get, right, I take the second time derivatives of this, all right? So here I have a minus omega square, right? Minus because I have the imaginary unit. This matrix MIK, this mass matrix, plus here I don't have anything. I just have these constants that I call, I mean, these are so like the spring constants of this system, K sub ik, okay? And you see then the derivative of the exponential gives you back the exponential, so essentially you have the ak equal to 0, right? Because this is never equal to 0, so I can simplify it. Are we all on the same page, or? Yes? Okay. So as I said, from a differential equation, through this neat trick, I get an algebraical equation that, however, I have to solve. And you see it's a system, right? Because I have I, so this is 1, 2, 3, 4, and then it goes like this. Now, what is the condition? So this has to give you 0, right? And the unknowns are these frequencies. And what is the condition for a system like this to give you 0? Is the condition that if you want, the eigenvectors are not linearly independent, or in other words, that the determinant vanishes, right? That's the condition for the vanishing of this. So a non-zero solution for this system, okay? There is also the trivial zero solution, implies that the determinant of this quantity, so the determinant of, well, let me write it in the other, just the sign is immaterial, vanishes. So from your linear algebra, you know this. So if you want to solve this, the condition is simply that the determinant must vanish. And you see, now you have an equation in omega square, right? Because these are matrices. You take the determinant, right? It's going to be a characteristic equation of a degree that depends on how big these matrices are, therefore by the number, depends on the number of degrees of freedom. Then you solve that, you find the roots of those, and those are the characteristic frequencies that are going to give you the solution. And that, yeah.
Omega depends on the K or not?
The omega?
Yeah.
No, the omega does not depend. Well, it depends on, okay, it depends on K, yeah. In a sense that, if you have, well, you'll see in a second. When we do an example, it will become clear. Then the general solution is going to be a superposition of these solutions for each of these different omegas. So you are going to have as many omega as the solution of this equation. And that depends, if you wish, on how many of these things you have. Then the general solution, you can write it as a superposition. So you have, maybe I write it this way, that so you have this amplitude A of K, and each of those depends on an omega, okay, in a solution that I call like this. And so I call omega of alpha the alpha solutions of this system, and therefore each of those has as a function of time, this exponential, and you have alpha of those. Okay? This is another nice things, right? That these kind of systems are called linear because the general solution is just a superposition of the individual solutions. That's a nice property of linear systems, that if you have two solutions, the sum of those two solutions is again a solution. This is not always true. I mean, it's only true for systems described by linear differential equations. Okay. If you have this solution, so now this is the general solution. Now it may be a little bit cloudy at this point, but in a second I will work out an example that makes things a little clearer. I just want to write the general solution for a general problem so that we know. You see, this is the general solution, but it's not very handy because you have a solution in which you have pieces oscillating with different frequencies, right? As many frequencies as the number of degrees of freedom. Okay, so that's a solution, no question about that. But it's a weird superposition, and clearly you can solve the problem in using you can do a coordinate transformation in such a, so you go from this xk to new coordinates that I call theta, I don't know, alpha, where alpha reminds you of the fact that I want coordinates. Each coordinate is such that the solution in that coordinate moves with a single frequency. That means that in this coordinate, the equation of motions are not like this, they are not like this, but they are each like this, right? This is always possible, you understand, because if you remember your linear algebra, I can always find what is called the diagonalization of these matrices, right? You diagonalize the matrix. You know about that. You have done that in quantum mechanics all the day, right? All you do is diagonalizing matrices, I guess. And you see that if you diagonalize these two matrices through some rotation that is a change of variables, then this system decouples, right? Because you don't have crossing between different coordinates, because by definition the matrix is diagonal. So each coordinate talks only to itself. And that means that this set of differential equations that are coupled become a set of alpha going from 1 to s of decoupled differential equation, that each of which is just an harmonical oscillator with that particular frequency. You see the beauty of this? You start out with a system that is all interconnected and assumedly very complicated. But your linear algebra guarantees you that if this is the case, you can always change these coordinates to a new coordinate that I call big theta here, in such a way that each of them doesn't see the others. And it oscillates like a happily uncoupled harmonical oscillator. Now these coordinates are the normal coordinates that I refer in the problem. So actually, every time you have systems like this, the usual problem asks you to find the normal coordinates, so to find the transformation from your generalized coordinates x to this new set of generalized coordinates that you identify to be the normal coordinates. This is a very powerful thing, because you see it's highly non-trivial, because you are not diagonalizing just one matrix. You are simultaneously diagonalizing the kinetic term and the potential term. So if this is possible, you can write your system as simply a sum of independent harmonical oscillators. So the problem then is just, yes.
Matrix K is not a diagonal matrix.
No.
K.
It's K-I-K, so in general it's not. If it's diagonal, I will write it like this. You know this symbol, the Kronecker symbol. Do you or you do not? You do? Do you? This symbol, what is it? And it is a matrix that is 0 everywhere except on the diagonal. So if this is diagonal, then I can write it like this as a constant, but I didn't do it. Okay, so let's see an example, so maybe it becomes clearer. So first a purely mathematical example, and then we address a physical problem with this technique. So I just write an example of a system of differential equations, right, with constant coefficients. Let's say, let's study the next to the simplest one, right? So the simplest one is the one we discussed on Wednesday, where I only had one coordinate. So this was a peculiar matrix with only one by one matrix. Let's do, so for instance, 2x double dot plus omega square. So I already normalize everything, okay, in such that I only have and 2. So this, so the M I had here, for instance, okay, it's a very simple case in which the M's were all equal and the K's were all equal. So I divided and I called this omega is just the square root of K over M. Okay, so this is the simplest. I took a matrix here, but the M's are all equal and the K's are all equal. And you see, this is, okay, it's just a mathematical problem. So how do we solve this system? Well, as I said, I plug in a test solution, right? And I have x, so I call my x, I don't know, a e to the I alpha. Remember, I wrote the xk was some amplitude depending, e to the same frequency. So y is going to be, I don't know, b, because the amplitude may be different, but I put the same frequency of the motion, right? In fact, you can write this as a vector, so this should resonate with your linear algebra that you solve this by, I mean, really the solution is a vector, right? A vector that is in this form. But, well, I don't know, some students prefer to think of this as a vector, some like this. It's exactly the same thing, obviously. So if I take this and I plug in my differential equations, you see that I get 2a. Now here I have two derivatives, so I get minus alpha square, as I was getting this plus 5 omega square a, because I have x, minus 3 omega square b, because I have y. Everything is multiplied by e to the I alpha t. I can drop that, and I get 0, right? And by the same token, I can now I get b minus alpha square plus 5 omega square b minus 3 omega square a equal to 0. So again, this nice Fourier trick, I trade in a differential equation for an algebraical one, and now this I can solve, right? I can solve it, and maybe let's put it in this form here again. You see, this is a matrix. This is a matrix with this entry, right? With minus 2 alpha square. So I want to look at the A. So plus 5 omega square. Then I have a single entry minus 3 omega square B. So you see, I want to write this in this form so that it becomes clear or clearer what I'm doing. So here I want the coefficient of A, and then B has those two terms. Right? So these two are completely equivalent. I just, if I do the product of this matrix by this vector, I get exactly the first equation. If I do this by the same vector, I get the second equation, right? You remember how to multiply matrices. It's a weird thing, you know, I mean, but that's the way you have to do. And here you do the same, but this is just a one-dimensional matrix, also known as a vector. And again, you know that for this to have a solution, you require, as we did in general, the determinant of this. So I take the determinant of this. So the determinant of this must vanish. Okay? And so what is the determinant of this? Well, you know that you have to multiply that minus the other one. So if you do that, well, I've done it for you. I get 4 alpha to the 4th, clearly, because you see you have this times this. Then you have the mixed terms that they sum up to 20 alpha square omega square. And then you have a bunch of 25 from here and then 9 with the opposite sign, so 16. So 25 minus 9 is 16 omega to the 4th. So the vanishing of the determinant gives rise to this characteristic equation. And how many roots do you have? So well, it's the 4th order, so in general it's going to have 4 roots, But you see it's a peculiar fourth order because only omega square enters, not omega. So you are going to have these four solutions are going to pair off in plus minus, right? Because they are all solutions. In fact, if you try, you see that, I'm sorry, yeah, what I'm doing. I have to, yeah, I got confused with this omega square. I have to solve for alpha. So again, it's the fourth order, but again, I mean, everything I said is true, but I switch it off. And so I found alpha, I have, well, you see almost by inspection, you see if alpha is equal to omega, right, you get omega everywhere to the fourth, and then you see minus 20 plus 4 is exactly 16. So plus minus omega is a solution, and the other one you can check is twice that. So the other two solutions are plus minus 2 omega. So if alpha is equal to one of these values, then you have a 0. That means you have solved your equation. Therefore, your solution, you see, you are going to have two solutions. One for omega, for alpha equal to plus and the other one for alpha plus minus 2 omega. And how do you write those? As I said, you have a superposition of all those solutions, and you can also find the values of A and B for each of them. And you know that this is, I mean, once you have the eigenvector, you can find once you have the eigenvalues, you can find the eigenvectors. And you do that by plugging this back, and it's easy to verify that, you see, if you plug this solution in your equation, right, then you see that this leads to A equal to B to be true. While if you plug this one, you get A equal to minus B. Do you see that? You see, plug alpha equal to omega. You want to find the eigenvectors of this problem. So here I have omega square, right, minus omega square. Then you see that you get, so omega square is everywhere, and here I have minus 2 plus 5, that is 3. So you have 3a minus 3b equal to 0. So for that to be a solution, you need a equal to b. Okay? So this way you find the, are you familiar with this thing of finding the, I hope so, because it's not my task to teach you that, just to remind you. But if you plug the other solution, 2 omega, right? You plug 2 omega in here, so 2 squared, this is 4, right? Then you have 8 minus 8, right? You see, so then you get minus 3. So for that to be a solution, A must have the opposite sign of B. That is what I wrote there. Okay, this is the way you... So the eigenvectors, so of course this only tells you the relative weight of this. You have always an overall coefficient that is free. This is going to be fixed by the normalization, but let's not worry. So this means that this eigenvector is A equal to B, so it's 1, 1. Then you have an overall that I don't care for the moment. And the other eigenvector is this one. Eigenvectors are important because they tell you how the system is going to move. Because when you write in terms of normal coordinates, those are going to be the eigenvectors. And you see, the first solution tells you that x and y moves in the same direction. So they oscillate like this, or like this. I don't know how they are. And the other one is that x and y oscillate in the opposite direction because the eigenvectors has opposite component. So that will is your key to the visualization, well, I can say it, to visualize the solution, as we will see in a second. So how does the general solution of this mathematical problem well, this we already use it. So here I can write the solution. I can write it in this, is a vector, so in this form. And as I said, the solution is the superposition of all your solutions. So I have two solutions with some amplitude that I said is arbitrary. This is going to be fixed by some normalization. If you normalize the modes to have, I don't know, the sum of the square of the amplitude equal to 1, you fix this coefficient. Or you fix this coefficient by the initial conditions. You see, is in this form. This multiplies this omega t, but you also have the same eigenvectors with the opposite frequency, because this is associated with both plus and minus omega. Plus, you have a solution with the other eigenvector, the one with the opposite signs, and they go like 2i omega t, and of course, minus 2i omega t. So this is the solution of this equation. If you wish, you have 4 arbitrary constants that you can fix by fixing, for instance, the initial velocities and positions, or by normalizing or whatever. But this is the, okay? Actually, you can make it a little more compact, because you know that these solutions better be real. So here you are not guaranteed that this is real, because it's a superposition of imaginary, complex functions. So you are not sure. So actually, you can require them to be real, and that actually sort of fixes 2 out of 4 of these constants, because you understand for these things to be real, you need that the sum of these two give you something real. So that means the conjugate of A2 must be equal to A1. And similarly, you need so I wrote twice 3. I guess this must be a 4 otherwise. And the conjugate of this, okay, so what I'm saying that A2 star must be equal to A1, and A4 star, so the conjugate of this must be, if this is true, you see that these two, you see this is the conjugate, so the overall is the conjugate, therefore is the real number plus the conjugate, this is the cosine, right, if you remember. So in other words, now I can write this, so let's call, I have A1 is equal to A2, conjugate. So this is what I can, it's a complex number that I can call now B1 e to the phi 1, right? If I give this name, then these two combine nicely in a B1, 1, 1. You see the cosine of omega theta plus this phase that I introduced. So this is a complex number in general that I write in this form by using this, how it's called, the polar representation. And because of this requirement that this is equal to the conjugate of that, okay, then I can write it as a cosine. And similarly here, I can do the same. I can call this 1/2 B2 e to the I, another phase, phi 2. I put a 1/2 so that I get only the cosine, B2, 1 minus 1 cosine. So the sum of these two is the general solution of this system. And I'm done. Okay? So let's see now an application. Is this procedure clear or? So this was just a mathematical example, but let's see. So in the problems, in the homework, you have two more examples where you are supposed to apply this technique, and let's see how it works in a physical context. So I guess here I have a. So usually, as I said, if you think of atoms interacting, and they interact with the forces that look very much like springs, right? So the simplest, think of the simplest non-trivial molecules, something like, for instance, water, H2O, I guess, right? You know about this, the thing you drink. Okay, this is a 3 atomic, right? Because there are 3 atoms, 2 hydrogen and 1 oxygen, and the oxygen is much heavier than the hydrogen. So it looks like something like this. Actually, it doesn't look like this, but so you have the oxygen here, and then you have 2 hydrogens. So I call the mass of the hydrogen little m, and the mass of the oxygen big M. Actually, it's not like this. Yeah, it likes to be some more like this, I think, because atoms, molecules always tend to minimize the energy, and that minimize the energy. But never mind. This is just a configuration. Let's look at this problem that somehow is inspired by, but there are other molecules that looks like well, never mind. Chemistry is not my. Okay, and you see that the force, of course, the forces, you don't have springs there in the. You have sort of electrostatic forces, right? But to a good approximation, any motion, so there must be some equilibrium position. Remember what we said about the potential. So here there is a complicated potential. That complicated potential that I wrote there, you have 3 coordinates. So it's a potential may be complicated, and it's certainly complicated if this guy start pulling like crazy away, then you start feeling a very weird potential, right? But as long as they behave, they well behaved, so they move a little bit, maybe a little bit down, maybe, so they move a little bit away from the equilibrium position, is well described by an harmonical oscillator-like potential that in this picture I draw a spring, okay? Meaning it's a force that is proportional to the displacement. This seems to be a force that is very common, as long as you stick to positions close enough to the equilibrium, right? So this is a general rule. I mean, if you are close to the equilibrium, you move away, there is a force pulling you back to that position. Because, it's like if you are all well organized, like in this class, if he starts moving, then there is a force that is somebody telling him, just go back, and he must go back, because it is perturbating the entire system. This way you are at your ground state, right? But you start, like kids, he runs there because he wants to talk to his friend. And then that no longer the minimum in energy, right? It's a higher state, and everything likes to go to the minimum of energy, especially the teacher. So you see that this can be described by what we have said up to now, because if I write, so let's write the potential in this assumption. So let's make also the reasonable assumption that the force between this and this guy is essentially the same as this, and that the other guy. Then if I call this, say, x1, x2, and x3, by this I mean the positions of this okay. So I want to make it really simple. I really want, So I don't want to study the case. I think maybe so let's just study the case in which they oscillate, but they remain on a line. Okay, I want to make things easy, so that these are really coordinates, right? Because if I give you that, you know where this is. So you cannot move out from the blackboard, neither in the plane of the blackboard. So then, under this assumption, you see that I have a potential, right, that is just the x2 minus x1. So maybe I put here also this rest position. So B is the distance at rest, at the minimum, right? And then x1, x2 there, and it's square. And then I have the other. Please. Well, because so I mean, I start counting, I don't know, from, so I have a common B. I mean, you can put it or not. It's up to, it's not going to change the equations of motion, as I've told you 100 times. But, so you want this distance, you can have a B, you know, it's from where you start counting. But, okay, if you feel uncomfortable, you can start counting from actually, okay, it's a little more, I want the rest position in a way, right? I mean, because, so x1, x2 is this distance here, right? You start counting from here. Then they push back and forth, right? But there is a rest position that is when x and 2 are equal to B, there is no more potential. That's why I put the B, really. But again, since it's a constant, you can drop it. But you see why it's there? I mean, you have a spring. The force is proportional to the displacement. But there is a position, a value of this displacement for which the spring is at rest. It's not pulling any longer, right? And this is the value that I call B. If x2 minus x1 are such that this is B, I'm sorry, that this is B, then there is no force any longer, it's at rest, okay? You're familiar with the fact that spring is not pulling all the time. It pulls only if you pull away more than a certain distance at rest. That is called, well, I call it here B. Yes, no? If no, just drop the B. If yes, keep the B. I mean, it's not going to change the equations, but physically, you want this potential to vanish for a value that is not x equal to 0, because that would mean that they are just zero distance in the spring. At a certain point, the spring is not working any longer because it's at rest, there is no pull. Then you pull further, and then you start working against your pulling. But in fact, we can get rid of that. Let's just put it equal to. And also, you see that I really want to change variables to some eta I, such that well, anyway, if you put b equal to 0, then these are okay this way, I guess. So if you write this potential now, it's going to be k over 2. Then you simply expand, right? So it's going to have x1 square. You see, you have twice x2, so 2x2 square plus x3 square minus the double products. Okay, and what is the kinetic energy of this system? Well, there are just 3 particles, so this is the potential. The kinetic energy is just, well, 2, this one, yeah. You were said. So it's just m divided by 2, then x1 dot square plus x3 dot square, right? Plus you have the oxygen, that is the big guy, that is x dot 2 square. So here's the Lagrangian, right? And as you by now know, I mean, after you have the Lagrangian, then you are in business, because you don't have to worry about the intricacy of this system. You just write the differential equation. And what is the differential equation? Well, the differential equation is just in the form that we wrote. This time is going to be a matrix with how many components? So these are symmetric matrices. We have 3 by 3, right? So it's a little more complicated than what we discussed in the mathematical problem. It was a 2 by 2, but it's the next level in complication. In fact, okay. So you can write this the Lagrange equations now, and if you do that, well, you get right here second derivatives equal to those, but you can already plug in. Remember that you only need to solve this problem. All you need is the determinant that I wrote in the general form by this, right? You only need to find the 0 for this determinant, where the determinant was of a matrix given by this k. And what are these k, ik, mik in this case? You see that they are what? For instance, the miks, you see m11 is m, right? M, okay? And this is big. So I can write this in what form? K, you see, you have this. This is the structure of the matrix in K. So the 1, 1 is K, right? K. Okay. But you see, the 1, 1 is K minus omega square, the M11, that is M, right? So this is so it's a 3 by 3. The 1, 1 entry must be this one. What is the 1, 2 entry? The 1, 2 entry is not here, because this is, you see that it's diagonal, right? The kinetic energy is diagonal. You only have the 1, 1, the 3, 3, and the 2, 2 element. But you see that the potential is not diagonal, because there is some mixing between the. And in particular, you see that I'm looking at the 1, 1, 2 is this one, so 2, 2, so it's just minus k. Okay? You see what I'm saying? I don't want to write everything. I know what I need, so I just extract from these two the form of the 3 by 3 matrix, and then I take the determinant. How about the 1, 3 entry, so this entry here? As we said, the kinetic energy has no entry. The kinetic energy, we can write it immediately, is just a diagonal. Is 1, 1 is m, right? Then, okay, but let's. So what is 1, 3? Is there a 1, 3 in the potential? No, there is no mixing between the coordinate 1 and 3, because there is only mixing between 1, 2 and 2, 3. So here is a 0. About then, so this is what 1, 1, 1, 2. 1, 2, again, it cannot be in the kinetic energy that is diagonal, so the 1, 2 must be here. Right, 2, 1. But the matrix is So you don't have to compute this. You only need to compute half of the matrix.
Sir, do we have a factor of half on 1, 1?
No. You extract it from here. You can read it off from here because
No, K.
no, the same here. You can read it off here.
1, 1.
No, but okay, but this is the potential. So you must. Okay, I see where you got confused. This is the potential. So I have to take the partial derivative. So I have killed okay. So I effectively a factor of 2 that I'm splitting between these two terms. Okay. So I keep on going. So now we agree that I only need to compute this half because this is going to be symmetric. For instance, if I have a 0 here, I have a 0 here. The 2, 2, however, has a component from the kinetic term, right, that is minus omega square big M, but it also has a component from here because of the potential that is just another K. But actually, you see, you have, because you have a 2, is a 2K, right? How about this? This is 2, 3. So 2, 3, okay, no kinetic energy because it's diagonal, but I do have this term here. I do have this term here. Okay, and this gives me a K. And immediately I can put it here by symmetry. So I'm left only with a 3, 3. No, 3, 3. I have a kinetic term, and I also have a 3, 3 here. So it's just equal, right? I mean, these two are completely symmetric, these two. So it's just equal to 1, 1. So this is the matrix of which I take the determinant and I put equal to 0. So are you all happy with this? Or if you are not, then, no, I mean, seriously. You take the Lagrangian, take the equation of Lagrange, okay, so that you see where all these twos go, and then write from the equation of Lagrangian, write the matrix. Okay, I skipped a step because, I mean, you can guess what they look like because they're so simple, so that we can finish in time. Now, so you know how to compute this determinant, right? You go by line, or you fix one, and then you take this determinant of the submatrix, that I guess is called the minor or something, and it's always clever to start from a line that has a 0, right, in a way, because that's the one step less. If you do that, let's put it up here. I guess you should get what I got, that is omega square k omega square little m times the cross product that is k big M plus 2m minus omega square big M equal to 0. So now I can erase, that's all the information I wanted, so I can erase this matrix that in fact, I don't need the potential any longer. And I guess I keep my little drawing. So what are the solution of this? So now actually it's omega I'm looking for, right? Omega is my unknown. Immediately you see that if omega is equal to 0, then you get 0. So the first root is omega equal to 0. The second root is if this term vanishes, right? So let's call it that omega 2. This to vanish, I need the square root of k over m. And then if this last term vanishes, that is my third root, this vanishes if you check if k over m 1 plus 2 little m over big M. Plus or minus. because, yeah, you're right. I mean, this is a little odd, right? I mean, frequency equal to 0. What does it mean? This is a periodic motion with 0 frequency. I mean, it's odd. But you understand what that must correspond once we have written down the normal modes, because you do have a solution in which this molecule just moves as a whole. So when in this kind of problems you find a 0 frequency motion, that corresponds to a translation. So it's not a periodic motion in which something is oscillating. It's just as a whole, the center of the mass of your system is translating. So we will. So if you wish, this is the center of a mass motion, and these are two frequencies instead that we are going to see. So this in a way this is the solution, but I want to find the eigenvectors as I did before, because the eigenvectors are going to tell me what I just told you. For instance, that to this frequency you expect 3 eigenvectors all pointing in the same direction, right? So that the motion is just a translation along that axis. So let's try and find the eigenvectors, and then we stop. So how do I find the eigenvectors? Well, I have to plug in my matrix, right? That was, you remember, k square minus omega square m. But here I put a apex j because I want to remember that this term multiply the eigenvectors, say a1j, okay? So I take my matrix and I multiply by I call it a1, a2, a3, okay? But I have 3 of these, a1, a2, a3. So I need another index here to remind myself that this is the JA1. Okay, they all look the same, but this is a 1 and this is a J. And this is a J, that means this is the vector, the eigenvector related to the eigenvalue omega J, that may be 1, 2, and 3. Yes? So I multiply, well, I don't know, maybe I shouldn't have erased this. So maybe I had this matrix, right? 0, minus k, 2k minus omega square big M, minus k, 0 minus, let's see, make it 0 minus k, k minus omega square m. Okay, I had this matrix. How do I find the eigenvalues? Well, I call each eigenvalues, so I call this component A1, A2, A3, okay? So this is the but the eigenvectors depends on what eigenvalues I put there. So I call these eigenvalues 1, 2, 3, I put a J, and therefore this is a J that carries to this. And this must give me 0. This is the way you find the eigenvectors, I'm sorry. There is no shortcut. So now I'm writing the first, so I take this, I multiply, and I look for the 0. So I'm writing this. So I wrote only the first component. So now I write the second component, that is just minus k, a2j. Then the third component is simple because it's 0 times something that is still 0. So this is 0. So if I solve this, when I plug in, for instance, omega 1, that is 0, I found a1, a2 for the 0. But I have to write also, let me write also the second. Now I take the second. I have 3 equations. I take the second row, and I multiply by this column, okay? And if I do that, you see that I get minus k a1j, right, plus 2k minus omega j square big M times the A2J, and this time I also have minus K A3J equal to 0. Okay? And now the last one, that is minus K A2J, right? Plus K minus omega square J little m A3J equal to 0. Okay, so this is my system now. This I rewrote it only to explain what I was doing. Okay. So now let's consider the eigenvector for the first eigenvalue. That is, I take omega equal to 1. Now omega equal to 1 is 0. So you see I have this equation in which I think this was a k, right? So essentially, what is this? So this is 0 in this case. Well, let's write it. I have, well, right, okay, thank you. So A11, because now J is equal to A21, and I can do the same here, right? And you see that by the same token, A31 must also be equal to A21. So they are all equal. So this is the eigen. So okay, it's like 1, 1, 1. How about the second eigenvalue? That if I plug here omega 2, you see omega 2 square is k over m. So k minus k over m times m, 0. That implies the A2 must be 0. Everybody, do you agree? No, you don't agree. Why? So now this is done. Now we are doing this. So plug omega 2 in here. So you get the square of omega 2, so you get k over m. K over m times m, k minus k, 0. So this is gone. The only way to satisfy this equation if this is equal to 0. So A22 must be equal to 0. Clearly, the same is true here, because it's essentially the same. If I plug here, this goes to 0, and this is A22, so it's similarly satisfied. What happened? So what happened to what is A12 and A32? Well, this I can derive from here, because if I now plug in the solution, what do I get? No. Let's do it. So now I have minus k A12, right? No, plus 2k minus, let's do it, k over big M. So there is a 2 here, so it doesn't, times M. A22, T2 is 0, but minus k A32. So this means that, okay, this I already, but then it's minus, okay? So this is gone, thanks to what I did before. Then I have minus k A12 minus k A32. So they must have the opposite sign. So A32 must be a minus A12. Finally, I can plug in the more complicated one, that is omega 3, okay? And so if I do that, you see that well, we have to do it. So if I do the first one, you see that I get well, so k minus km1 plus 2m big M times m, right? So I get k minus k, right? That simplifies. So this simplifies with this. Then I have k minus k is gone. Minus, so this is minus 2 m big M. This is A13 minus k A23. So this is one equation. And from the one downstairs, I get something similar, right? Because now I decide that this combination is just minus 2m, so I must get minus k A23 minus 2m big M A33 must be equal to 0. So that's two equations, and I still have to do something with the one in between. A13, A23, okay, A1, 2, 3, A33. And this one is minus k A13. Then I have this other combination that is 2k this times big M, right? Because omega is still this. So this is a little different. I have to collect them. So I get plus, so minus k A33 plus 2k is this thing. So I don't know, what is it? So you see, this is, so it's 2, so this cancel, so it's minus 2 is gone, right? Come on, don't give up now. We are almost done. So this is minus k big M over M, right, the first term, minus what? 2k. Then 2k, this is gone, so I have just minus k m little m that multiplies this A23. Okay, so now we can solve this system here, and we get the last eigenvector. So these were the first two. And you see that this to be solved, well, A13 must be equal to A33. A1. Eh?
Because it is symmetric, we have
What?
because it is the metric is symmetric, so why we have A32, then we know A23.
No, why? You have to solve it. No, it's not obvious. It's symmetric, but anyway, you see, if take these two, right? And actually, if you change the sign and sum, right, then you see that A13 must be equal to A23, A33, right? Because you change sign. These two simplifies. Then you have this sum with the opposite sign. So A13 must be equal to A33. Then you can plug in here, right? So these two are equal, so you get their sum, and you get A23 that is equal to 1 over 2m, 1 plus 2mm. Mm-hmm. So, what did we learn? Well, now I can go back and confirm what I said before without proving it. So now let's look at the modes, the normal mode that is described by this coefficient for the first eigenvalues. You see, this is a mode in which your vectors, each component, are pointing in the same direction. So it's a motion like this, right? And they have the same amplitude, right? There is an overall that I have to fix. But so as I said, this is a motion in which your H2O simply translates in one direction or on the opposite direction. So this is the motion of the center of mass. How about, so this is not that interesting. How about the second eigenvalue? The second eigenvalue, so this is the first. The third is this. It has A22 that is 0, and A1, 2, and A3 that are in the opposite direction. So what is this motion? So A22 corresponds to the motion of the big M, so that's 0, so it's not moving. And the other two guys, they are moving in the opposite direction. So this is the motion like this, right? So first motion is this is the motion like this. How about the third one? The third one is similar, right? It is a motion, but you see here you had the minus, so it was in the opposite direction. The other motion is a little, so you have here the the A22 moves by a certain amount in a direction. I think there is a sign that I don't. A13, A2. So this, sorry, this is -2. I made a mistake. So this is a motion that is like this. This is moving by a certain amount in this direction, and the other two moves in the opposite direction by the same amount that is different from this one. So this is a motion a little bit here, and the other moves in the other. And you understand that it's like, because this is heavier, this moves much less than the other two in the opposite direction in a certain, that is proportionally to the difference between the two masses. So what are these? These are the normal modes. These are modes in which this water molecule is oscillating with a fixed frequencies. So these are not superposition. The general motion is a superposition of this. So in general, it will move like this because it's superposition. But this is a superposition of these three fundamental modes, one in which is moving like this, one in which is moving like this, and the other that, I mean, I cannot do it, that is moving a little bit like this and like that, okay? And so just to finish, well, okay, you can maybe try yourself. So now you can go to the normal modes and change your variables to the normal modes and see these eigenvectors as they move. But okay, maybe you do it in one of the exercises. Okay, so that's all I wanted to say. Really, it's useful to solve problems of this. In fact, I gave you 2 problems, I guess, or 3 on this, and so on Monday we do some more on this kind of systems. But I hope you see that it's a very powerful technique too, because it allows you to solve problems that in principle looks very complicated, right? I mean, a bunch of atoms oscillating in a different way, different various ways. You can also make it more complicated if you allow them to move on the blackboard plane, right, or even outside the. But clearly, this matrix become bigger and bigger, and then you require some computers to do the things. But okay.